Okay. Hello, everybody. Happy whatever it is today, Wednesday. So today's lecture was a lot. And I got tired watching it. So I can only imagine how you guys all feel. So let's break it down and do it SI style. So last time we talked about chemical shift. We talked about all the different hydrogen regions. And I told you guys to look up the carbon numbers in the PowerPoint because they're available. They're not really something you have to focus too much on. The only thing you have to know about carbon NMR is the little note here about the carbonyl region. So who wants to explain back to me something that we talked about with this stuff? Yes. Perfect. Yes. So resonance effects are stronger than induction effects. And we saw that on the carboxylic acids, it had the stronger resonance effect. And then this one had one inductive effect. This one had two. So we did definitely talk about that. What else? Yes. Yes, so I want to be careful when I say that because some people are then like, okay, well then, does that mean induction is stronger? No, resonance is always going to be stronger. However, in hydrogen NMR, that means the carboxylic acid is the most de-shielded. But in carbon NMR, that means the carboxylic acid is more shielded. And that has to do with resonance effects in both cases because here, the hydrogen is chilling and all the electrons are resonating that way, far away from the hydrogen. Whereas here, all these electrons are resonating this way and they're going right over that carbon. So the carbon is snatching up some electron density as resonance is happening. Any questions about that? No? Okay. I don't know if I've given you guys this whole spiel yet. I'm not going to bite you. I promise. I'm never going to be mean to you or judge you for asking a question. And I would rather you ask me a question now and feel a little bit embarrassed than that question come up on the exam and you get it wrong. So I think I'm pretty friendly. I'm not going to be shady if you ask me a question. The only thing I will probably be shady if I'm like at the last like 2 minutes of my SI session and you're like, wait, repeat everything. Because that has happened. I will not repeat 50 minutes in a minute. That was supposed to be a joke, but I just said it really flat. Yeah, what's up? No. Okay, but someone said something. Okay, so we're going to do this question to kind of review what we did last time. So all the question is asking is in a carbon NMR spectrum, which of the following would be the furthest downfield signal? So I'm going to add a little bit more to this, and I'm going to say put these in order from most to least de-shielded. All right, and we're going to do really fun partner activity. So all of you guys can be in a group. You guys can situate yourselves as you see fit, and then you guys on that side can all be a group. And I'm going to give you like 3 minutes, and then we're going to talk about it. Okay? Did we do this one? No? You're just ahead of the game. All right. Start chatting. Come on, socialize. Ow. Do it. You show them how smart you are. Just rubbing them together like, whoo. No. No more of this. Yeah. I'm sorry. I need to do something to keep myself entertained. I have one for chapter 9, but it's for next week. I'm way too behind. I feel that. I'm so sorry. It'll be back in a second. I'm a monster. Mm. Okay, guys. So you guys are working so well together, and I really don't want you to stop, but I don't want to spend too much time on this question. So is everyone okay with going over it now? Are we good? Is anyone super not willing? Anyway, why are you being this way? No. Okay, good enough. All right. So someone tell me what you're thinking. Yes. Okay. Sure. Actually, I want you to give me the functional groups. We have to do some functional group practice. So you're saying that's the most shielded. Okay, so so these terms that tend to confuse people. So most to least de-shielded basically means we're saying most de-shielded to most shielded, right? So we're kind of going opposite of the spectrum, right? So let me just say it like that. De-shielded to shielded. To not de-shielded or shielded, we could say. All right, so since someone brought up the carboxylic acid, since Luke, because I know your name, are you guys saying that one is de-shielded or is it shielded? Okay, I love all of your logic. Someone said de-shielded, so what are you thinking? Anthony? Okay. So I am trying to trick you guys. This is a trick question. Kind of. Not really, but kind of. So you guys did say carbon NMR, cool. That one is more shielded. But you got to remember, this is still in the carbonyl range. So even though this is more shielded than this, that's way more de-shielded than this guy. So everything's relative, right? So when we talked up here about these guys, which one's most and which one's least shielded, we're still talking about all the way at the end of the spectrum. So like up here, when we have our most shielded and then we have our most de-shielded, all the carboxylic acid stuff, more shielded, less shielded, that's still within this region. And this region is way more de-shielded than all of this stuff, right? So I like where you were going with your idea. So carboxylic acid is more shielded than the ketone, exactly. But which one of these is the most shielded? Yes. So this guy is the absolute most shielded. So I'm going to say number 3. And it's the most shielded because it doesn't have anything electronegative taking away its electrons, right? So what comes after that? What's the next most shielded? Ooh, someone said alkene. The alcohol, okay. What region is the alkene in? We can also call it a double bond. The double bond region. And what is the number for the double bond region? 5 to 7. Cool. And then someone else said alcohol. So alcohol would be in the what region? Heteroatom. And the heteroatom region is 3 to 5. So between the double bond and the heteroatom, which one is more shielded? Heteroatom. So we're going to say 1 is next. And then which one? Then the double bond. Exactly. Cool. So after the double bond, what's the next region on our spectrum? Aromatic. And who's our aromatic friend? Benzene. So this one is up next. Cool. So now we're down to the last 2 slots, right? And you guys already told me which one is more shielded between the two? Carboxylic acid. So then the most de-shielded is aldehyde or ketone, but in this case, we do have a ketone. Yes. Okay, this was kind of bumpy, but because of like terminology and stuff, but how are we feeling? Cool. Okay, we're going to do a fun little thing. 0 means I have absolutely no idea what you're talking about to a point where I can't even ask you a question because I'm so lost. 5 is I could do this in my sleep. I want to move on. So I want you to raise your hand and give me a number 1 through 5 or 0 to 5. Okay. I'm pretty okay with that. As long as no one's at like a -1, we're okay. We can work from here. All right. We'll be back to this. Before we move on, I did want to show you this right quick. Don't look. Okay, this is stuff we'll go over in the future. I did promise you guys I would show you a pretty version of the chart because the one we did in SI was ugly. So if you would like to take a picture. Yes, I can. You're very welcome. Ta-da. Oh, I had to tell you guys something, but I already forgot. So never mind. Yeah, it does suck. No, it's gone. She got bored in there all alone. Anyways, are we good with this, everyone? Cool. All right. So go back to this. So this is where we're doing the really awful stuff, which is splitting. And we're going to do normal splitting first, and then we're going to do complex splitting. And I'm hopefully going to try and unmess the mess that happened in lecture, if possible. Okay, so first and foremost, what is the formula that we use to determine splitting and multiplicity? N plus 1. Wow. Okay, so splitting only occurs in what kind of NMR? HNMR, thank you. It does not occur in CNMR. Yes, you are smart. I don't know. Like someone right in front of me can be talking to me and it's like, but someone says something in the corner. I'm like, yeah, I heard that. Okay. Yes, laugh, feed my ego. Thank you. All right, so let's do some actual examples, shall we? I'm gonna choose to do, wow, I gave really bad ones. Yeah, I'll do this one. Okay, what's the first thing we look at for NMR? Symmetry, yay! Does this guy have symmetry? Oh, someone said no, but it is a yes. Bam. I'm sure you were, yeah. Okay. Yes, exactly. Sometimes, left and right, yes and no. Okay, there's also another type of symmetry in this. Kind of rotational, not really. Big word. No, but I'm glad you know what that is. Internal. I don't know who said it. I think it was Katrina. But yay. Okay, true. Well, then drink the water I brought you. Anyway, so these guys are symmetrical to these guys, but these are all exactly the same because of internal symmetry. So I'm going to draw this little thing saying that those are exactly symmetrical. So when we're counting signals, let's start there, right? I'm going to erase that for now because it's in the way. So 1, 2, 3. We said those are all exactly the same as these 3, which are also exactly the same as these 3, which are exactly the same as these 3. So what is the integration of the pink signal? 12. Cool. Next up is this guy. Does that hydrogen have any equivalent hydrogens? Yes, on the opposite side. So ta-da. And the integration is 2. Okay, next up, purple might be too similar, but you guys will tell me if it is. Okay, what's special about this position? It's a potential chiral center. Cool. So when we see potential chiral centers, what are we thinking about? Aneantiotopic, unless what is present? A real chiral center. Are there any chiral centers present? No. So what's the relationship between these guys? Enantiotopic, and they are both the same signal. So enantiotopic has a fancy name, but it's all just one signal. And we know that that is symmetrical to these guys. So what is the integration? 4. Swag. Cash money. You can call me Cash Money Rose from now on. Don't actually, please. Okay, so the last signal is these guys. And by this point, I'm sure you can tell me that the integration is 4. So the next thing we're going to do is go through and do the splitting for all of these. Okay. So let's start with the pink one. How many bonds can we travel to find a neighbor? 3, exactly. So 1, 2, 3, that counts as a neighbor. Is anything else within 3 bond lengths? No. So the pink hydrogen has, I don't know why I did this. I'm going to do it in pink. So it has 1 neighbor, which is the blue hydrogen, plus 1, because you guys told me that that is the equation, which is 2, which is a doublet. Super duper. All right, so the blue one has how many neighbors? Too many, absolutely. 6, why isn't it 12? Yes, I definitely can. Okay, so let's say we're talking about this hydrogen, right? This hydrogen is exactly the same as this hydrogen, correct? So we're only going to count one side. So we're going to say that this hydrogen has 1, 2, 3, 4, 5, 6 neighbors, and we know that the exact same thing is going on here, so we're just going to consider that 6 neighbors. Okay, 6 pink neighbors, I should say, not total. 6 pink neighbors. But I'm glad you guys jumped on that. So, okay, so what are the other 2 neighbors? Purple, because 1, 2, 3. Awesome. Swagnificent. Sorry, I make myself laugh. Yeah, absolutely. Yes, I'm just doing it this way so you guys see where I'm getting my numbers from. So you don't have to do them separately. I'm just doing like color coded so you know like where each number is coming from. Okay, cool. But that was a good question. So 6, 7, 8, 9. I know how to do math. So what is this called? A nonet or a multiplet, because we're all lazy chemists. Okay, so the purple hydrogen, you guys already told me that it has at least one neighbor, or yeah, the one blue neighbor. What else does it have? We are talking about the purple. That's it. Haha, good. Okay. So I wanted you guys to be like, oh, 3 neighbors, or these green ones, but that doesn't count because it's not within 3 bond lengths. You guys are, what? I do ask a lot of trick questions. This nice facade is just a facade. I'm really terribly mean. No. Okay. Where is my purple marker? Double it. Okay. Someone said, does she? And then I didn't hear the rest. Was that a question for me, or were you just like, okay, cool. Rewind. Yes. Okay. So when we're talking about the purple hydrogens, we know that we can only go within 3 bond lengths. And a lot of students will say, okay, 1, 2, 3. So these hydrogens count, except the hydrogen itself has to be within 3 bond lengths. So it only has this one blue neighbor. This one does not count. It's too many bonds. That's why it's just a doublet. You're very welcome. Okay. Green. So the green hydrogen has how many neighbors? 0. Yay. Plus 1 equals 1, which is a singlet. Cool. All right. Any questions on what we've done thus far? Yes. I'm absolutely so glad you said that. Okay. So n plus 1, n equals what? Number of unique neighbors. Exactly. So green cannot split green because it's not unique. It's exactly the same. That was a wonderful question. Anyone else? Cool. Okay, so now we have approximately 20 minutes to do complex splitting and hopefully unscar you. I relate. Okay. I'll try my best. Before we do that, I just want to mention something that Dr. West said. So we have something called spin-spin splitting, right? And everyone thinks that that's this big whole thing. All spin-spin splitting means is that you have a multiplicity higher than 1. So everything besides a singlet has inherently spin-spin splitting? Yeah. Exactly. So if he asks you a question like this, he just wants to know, is there at least one signal that has spin-spin splitting? So awesome. Let's do this one. Are there any signals besides a singlet? Oh, okay. One more thing we're going to have to talk about. So Dr. West in class today said that we're going to split through a heteroatom. This was news to me. I asked him about it, and he basically said that apparently the scientific community, blah, blah, blah. And now they're saying that theoretically, yes, we are going to split. So I guess I am required to relay that information to you. But he also said he's not going to ask you a question about that on the exam. So yeah, just keep it on the down low. Pretend you never heard it, right? For the purposes of this question, because I didn't go through and make new questions because I just found this out, we're going to say we're not splitting through the heteroatom for these questions, okay? Or else they're not going to make sense. So in this example, do these hydrogens have any neighbors? No, because of the heteroatom. Does this hydrogen have any neighbors? Yes, because it has these guys. So does this molecule show spin-spin splitting? Yes, indeed. What the heck was that? Yes. All right, next one. What's the first thing? Symmetry. Cool. So does this hydrogen have any neighbors? No, why not? Because it's exactly equivalent. This is the same hydrogen. So does this show spin-spin splitting? No. All right. This last one, it looks almost exactly like the first one. So do we just say yes and move on? No, why not? There's no neighbors. There's no hydrogen anymore here. And so the only hydrogens we have are all the way over here, all the way over here. So it does not have any neighbors. We did that kind of fast. So does anyone have any questions? Absolutely. So the only hydrogens present are these guys, which I drew as one hydrogen, and then these three, which I drew as just one hydrogen. So this is 1, 2, 3, 4, 5 bond lengths away. So there's no possible way they can count as a neighbor. So that means that both of those are singlets, which means we do not have spin-spin splitting. Okay. Yay. All right. So let's go to Torture Town. Ooh. Okay. Sorry, I wanted to respond with kinky, but I was like, I don't know if I can say that. This is being recorded. At this point, I don't care. All right. So, wow, you're leaving me? I'm just kidding. Fun. Okay, so, all right. So the first example, okay. I'm gonna even stand up for this warning. I'm gonna draw you some tree diagrams. No. So tree diagrams are wonderful for you to know because they help you conceptually. You will never have to make a tree diagram. Your tree diagram will never be on the exam. She said, hopefully. It's never been on the test before. You know, they decided to bring a new professor this semester, so they told us it's Dr. West exams. You guys get Dr. West exams anyway, but if anyone here is from Roche, no, thank you. Anyways, as I was saying, so I'm going to draw the tree diagram. I'm going to try to make it as simple as possible. It tends to help people understand the concept of splitting. But if I go through the whole thing and you're like, I don't understand what language you're speaking, forget about it and move on. Deal? Deal. Okay, cool. So we have 2 red hydrogens here because I said so. And we have 3 blue hydrogens here because I said so. All right. So Dr. West mentioned something about a J something and something something, right? So essentially, for the purposes of this class, all you need to know is that a J value is the coupling constant. Those words mean the same thing. And essentially, that is the value by which one hydrogen splits another. So I'll write that, yeah. I'm going to tell you which ones you got to know. There's only like 3 you have to know. Yes, I will repeat that and I will also write it down. So J values / coupling constants are basically the value at which one hydrogen splits another. And value is in terms of hertz. He went over a lot of like, if it's a ring, if it's this, if it's that, so many J values. Yeah, I don't know about you guys, but I'm not that enthusiastic about NMR. So I like to think same hybridization equals same J value. And it'll make sense in a second. Different hybridization equals different J value. And then we can take that one step further and we can say same J value is normal splitting and different J values are complex splitting. So I'm going to zoom out so you can see all of that. Okay, so we're going to start out with the red hydrogens and we are going to find the multiplicity and splitting of the red hydrogens. So these 2 red hydrogens are going to have a signal on the NMR, right? Conceptually, we know that, yes? Okay, so we're going to make that signal a line. That's all. And I'm going to make it a little bit thicker of a line. Okay. So conceptually, we can see that hydrogen exists, so we have a signal going. Each one of these neighboring hydrogens are going to split this signal into 2 signals. So I'm going to call this H1, 2, and 3. So this red signal is hanging out. H1 comes in and splits it like so. Bam. So I'm going to say this was H1, right? And this split happened at a very specific value, which is, it's the J value, yes. And in normal splitting, 9 out of 10 times, it's 7 hertz. So that's where the J value comes in, right? So now the H2 is going to do the exact same thing. So each one of these guys are being split into 2 signals. But look at that. We have some overlap. So the place that has overlap, I'm going to make it extra thick. Yes. Thick with 4 C's and a Q. Okay. You figure it out. Okay, so again, this value is 7, this value is 7, and this was H2, right? So now H3 is going to do the exact same thing over again. And I will go back up so you can see the whole thing. Drawing is hard, you know? All right. So this one is a regular thin line. This one has, what is it, the word called? Darn it. Overlap. So I'm going to make it really thick. It has the thickness. And this one is also overlap, so it's going to be thick, right? And then this one's normal. Yes? All right, and this is H3. So essentially, the one red signal has been broken up by each of its neighbors into multiple signals, right? Is that okay with everyone so far? Yes. Because I chose that one. So we can do this with any hydrogen here, and I just said, hey, this one's a good one. Let's find the multiplicity of this one. Yeah, you could do it with the blue. Then the blue would be the signal, and these two would be splitting it. Okay, so I just chose the red just because. All right, so now we're going to draw what this peak now looks like. And okay, the thickness of these lines is so much, it's so thick that the signal is going to be taller, like physically taller. So when we look at the peak, it's going to go something like tiny peak, big peak, big peak, tiny peak. Well, okay, so I'm drawing like what it would look like on the spectrum. And so yes, you get this from all the splitting, like once you're done with all of it. Yeah, exactly. And I drew it like correlating to these lines. This is what it would look like. 1, 2, 3, 4. And what do we call that? Quartet. Ta-da, you just did splitting from scratch. Yay! Does this like super not make sense to anyone? Yes. Okay, great question. So the reason these ones are thick is because it has one line from this side, one line from this side, and so it's two lines overlapping. So you can kind of think of it as two signals overlapping. So that just means it's a higher intensity because it's two overlapping signals. Well, just because this is the end product. Like this is just like the pathway to get to the end product. Okay, yes. Yeah. Okay, let's put a pin in that for 1 second and then I'll get to you. Yes. Okay. He's literally just gonna go, what's the multiplicity of the red hydrogens? Well, he might say like HA and HB. Like he'll make it obvious which one you're doing. Like he's not just going to give you this and be like, figure it out, you know? Does that make sense? Did I answer your question? Yeah, you would answer quartet, exactly. I saw your hand, yes. Yeah, so you can think of it as this is what's actually happening, and the n+1 rule is just a simplified equation that helps you skip this and just get the answer easily, right? Because we know this is a quartet, we know this has 4 peaks, but we could have also just looked at this and said 3 neighbors plus 1 equals 4. So you don't have to actually do this because the n+1 equation gives that to you simpler. Yeah, the tree diagram is just helpful to show you like where the overlap is and to understand that kind of stuff. But a quartet is always going to look like that. A triplet is always going to look like that. Not ugly like that, but you get the idea. I saw your hand and then your hand. Yes. What? Okay, we have like 4 minutes and there's another class coming, so I don't want to start that today. We will do that on Friday. Okay, yes. Wait, I saw your question first. No. For simple multiplicity, no. We haven't even talked about complex splitting yet. Oh, okay, yes, yes, yes. Okay, wait, everybody stop packing up for 1 second, please. Okay, is this what you wanted? Okay, cool. So I'll show you that for a second, and then just stay with me for like 1 second because I want to show you something and I don't want to waste time on it Friday. Yes. Yeah. Yeah, I know, so demanding. It's okay. I'm here, please. Oh, so sweet. Okay, so we're gonna go here. Bam, bam, ignore all of this. Okay. J values. To be completely honest, I do not care enough to go into more detail than just showing you this because that's a waste of all of our times. And I know one person is going to ask me, how would he ask you this on the exam? He will draw this picture and he will say, what is the coupling constant? 14. These are the only ones you should know. Vicinal is obvious. This is normal. You should know this one for sure. Geminal, once in a blue moon, pops up. W, once in a blue moon, pops up, but this is his favorite one. Sure. Yes. I don't remember the car plus curve anymore, if we're being honest. It's 180. Okay. Yeah. Yeah. Any questions? Cool. I'll be here if anyone wants to ask me anything. Have a wonderful day, and I will see you Friday. You are so very welcome. See ya. End meeting. Oh, yes.